Okay, folks, let's get started. It's my pleasure to welcome Dr. Thad Michael, who's today's speaker in our CNRE Winter Seminar Series. Thad is a naval architect at the Naval Surface Warfare Center, Carderock Division, and he received his PhD from the University of Iowa. He joined Carderock and is one of our experts, national and international experts in designing propellers. And he also works on related technologies at Carderock, where his work includes propeller design, water jets, twisted rudders for ships, evaluating fouling impacts on propulsors, and cavitation, inception, development, and erosion. And he really is one of the, he's a very good collaborator, works strongly with us, and what he does. So I'm really glad he took the time to speak to us and tell us about his work there. The title of his talk is Propeller Research at the Warefare Center, Carderock. Thad, thank you and welcome.
Thank you very much, Mahesh. Thanks everyone for coming today. As he said, I work for the Naval Surface Warfare Center, Carderock Division in the propulsors branch. And today I'd like to start by introducing myself and Carderock a little bit and tell you a little bit about Carderock Division for those who aren't familiar, and a little bit about propulsors. And then I've got a few short topics on propulsor related things that I'm interested in. And finally, I'll tell you quite a bit about our cavitation erosion project that's been going on over the last couple of years. And there's a lot about it though, so I'm sure you'll probably see another presentation on it in the future. Naval Surface Warfare Center, Carderock Division's part of the Navy. This is the mission statement. I won't read it all to you, but we do research and development and test and evaluation, and we support the Navy's ships in service, and in design. Wanted to point out that we have an educational partnership agreement with the University of Michigan, so we can work together under that, exchanging people and information and even laboratory equipment. And the Center for Naval Research and Engineering is a good forum for that collaboration, but we can collaborate other ways too. It doesn't have to be through the center, but I think the center is really an excellent opportunity to bring us together. Carderock has three major technical departments, and I'm going to tell you a little bit, well, one slide about each of them. There's the Platform Integrity Department, which I always thought of as a structures department, the Signatures Department, and then Naval Architecture and Engineering Department, which is the one that I'm in, and includes naval hydrodynamics. The Platform Integrity Department does a lot of things besides structures. They do materials and manufacturing. Some of the biofouling work is in there. They also worry about weapons effects. That's where these exciting pictures come from. They have a test pond at Carderock where they blow stuff up and see what happens. At least that's my perspective on it. They also deal with waste. One of the things they did was develop a machine for melting down plastics at sea, since we can't throw them overboard, to turn them into these pucks that can then be brought back to shore and recycled later. So they have a bunch of different things going on. I know people there, and if you want to get in touch with them, I can try to make that happen. The Signatures Department, there's a lot of different types of signatures, ways in which ships can be detected. There's acoustic, which you may be familiar with. There's also electromagnetic and other methods. They have some acoustic arrays out in the ocean they use to measure ships, and they also have some in a lake in Idaho that they use to measure quarter scale model, roughly quarter scale model. They also have facilities like this for measuring electromagnetic signature. So there's a lot of different and pretty interesting things going on there too. Naval Architecture and Engineering is what I think of when I think of ship design. They do a lot of the planning, that goes into designing a ship. Also, we have a lot of unique facilities. We have the towing tank. We measure the resistance of ship models. There's also a maneuvering and seakeeping basin where you can test maneuvering and waves, things like that. And we also have a large branch Division, I guess it's called, that it works on smaller things we think of as boats, combat craft, which are more commercial off the shelf, maybe with some modifications, rather than something we designed from scratch, completely custom. Where is Carderock? Well, there's a few places around the country, but the headquarters is near Washington, D.C. That's where we have the model basin that's like a half mile long that we can tow a model ship down. The maneuvering seakeeping basin you can't see in this photo. But there's also locations, like the one I mentioned in Idaho, the Acoustic Research Detachment. There's Alaska. In Memphis is where the large cavitation channel is, which I'm going to talk about during the cavitation erosion part of the talk. So there's a few different places around the country. As far as propulsor research and design, which is what I do, we design propellers not just for the U.S. Navy, but also other parts of the government. For instance, the National Oceanic and Atmospheric Administration asked us to design a propeller for one of the ships they use to count fish. And we've also done commercial work as well, and even foreign governments too. In order to design the best propellers, we need to be researching the relevant physics and developing new design approaches using our discoveries all the time. Because if you want to stay at the forefront of something, you've got to be pushing the envelope all the time. A question that I get a lot is, why do you custom design propellers for each class of ships? People ask me, I thought once there was one propeller design, you could just, put that on all the ships. And a point that I make to them, which I think is, relatively easy to understand, is if you spend $500 million a year on fuel for just one ship class, and you have several, then saving 1% is a really big deal. So just, economically, it makes sense to begin with. To put in some effort to try to save that 1%. I want to talk a little bit about different types of propulsors for those who may not be familiar. Up here on the left, that's kind of what we think of as a normal propeller. It's at the back end of the ship, and it's got 5 fixed blades spinning, and the rudder's right behind it. This happens to be the one for that NOAA vessel that counts fish. They want to avoid cavitation because it makes noise, and noise can scare away some of the fish, but it can attract other fish. And getting the fish count right is important for fishing rights. So this picture was taken. They dropped the pressure in the large cavitation channel so that you could see the tip vortex for visualization because it makes cool pictures. But in normal operation, it wouldn't be producing this tip vortex. Then here in the middle, this is kind of up and coming type of propulsion. We don't have any in the Navy yet, but we have been studying it. This is a commercial picture. Here, the ship is mostly to the right. And so it has a shaft-driven propeller, just like this one. But now behind it, rather than a rudder, it has a pod, which contains an electric motor and drives this propeller. And it can also be turned. The whole thing can swivel. And so that allows for excellent maneuvering performance because you can kind of pull it back into the ship in any direction you want to go. But also it recovers the swirl that comes off from this upstream propeller. The swirl from the propeller is kind of like wasted energy that you put into the flow from the torque on the propeller. And by passing it through another propeller that's turning the opposite direction, that just becomes like a beneficial inflow to this propeller. And then the flow going downstream should be more or less straight. And so that gives you higher efficiency. Ducted propellers are something that's been around for a long time. This is an old Navy ship. They're mostly used if you need a large amount of thrust per unit area, like they're commonly found on tugboats. That's what it allows you to do. This tip-loaded propeller is something new we've been experimenting with. It's kind of like what you see on the end of airplane wings, where they have the tip of the wing bent up. That allows you to carry more load out to the tip because you can't have a pressure difference across the tip where the blade ends, and this allows you to have a little bit more that can carry more load, kind of like the benefit of a ducted propeller. Loop propellers, this is actually a picture from the 60s. It's something we've looked into. It may make sense in certain applications. And then control pitch propeller hub. One of my coworkers suggested putting this in. In a control pitch propeller, you can change the angle of the blades around axis that runs, from the hub to the tip of the blade. They can be rotated by this mechanism inside the hub. And why would you want to do that? Well, on many of our combatants, they have a gas turbine as the prime mover, supplying power, and a gas turbine can't be operated in reverse. So if you want to go backwards or even slow down quickly, you need a way to reverse the thrust on the propeller, and swinging the blades around to the opposite direction will do that. So this is a picture of this type of propulsion, the counter-rotating shaft and pod. This was taken in our 36-inch water tunnel. It's being driven from upstream. This is the main propeller, and then this is the downstream pod with its slightly smaller propeller. Here they've reduced the pressure so that you can see the tip vortex coming off the upstream propeller and going over the downstream propeller. And in a minute, you're going to see this is a video. And there's a couple things it's going to focus in on. One is the tip vortex. Down here, you're going to see it interacting with this fin. And rather than break, it's going to be stretched and pulled down and around this tip. The other thing you'll see is out here, you'll see the way this vortex interacts with the leading edge of the strut that supports the pod. And you'll also see another vortex, a little thinner and at a lower radius. And that's actually coming from this second propeller here, the second smaller one. And you can't see it coming from that propeller, but as it approaches the strut, it gets stretched, trying to wrap around it. And as it's stretched, the rotation rate has to go up to maintain angular momentum. And you'll see that that causes a pressure decrease in the core of the vortex, and it'll become visible. So this video goes by pretty quick. I'll try to play it a couple times. This is at 39 knots. So here you can see the vortex going down around the tip of that fin. Just amazing the way the physics causes it to do that rather than just kind of split around the leading edge of the fin. Then here, of course, it doesn't have that option. It's gonna have to split. There's that skinnier lower vortex that I was talking about. Let me go back and see if we can get that to play again. Again, here's that skinny vortex from the smaller propeller. And this is a view from the other direction. The flow here is now left to right. I don't find this angle quite as exciting. Anyway, so that's about propellers. I also want to talk for just one slide about biofouling, since that's something I've actually been doing a lot of work on, and many of my other coworkers at Carderock. Why do we care about it so much? Well, ships that have reached the fouling threshold at which we'd say, okay, now that it's really bad, we need to go clean the hull of that ship. They might require 18 to 24% more power to maintain a given speed. And remember, we're talking about like $500 million worth of fuel, right, per year. So we we really want to keep them operating efficiently. And we would like ways that would mean we don't need to take them out of service to clean them as often. And so we've been studying the impact of hull fouling on propeller operation. And so when the hull's fouled, of course, the propeller needs to work harder to push the ship. But one of the surprising things is that the fouling, the additional drag on the surface, actually slows down the flow going into the propeller, and that appears as an efficiency increase. It doesn't make up for having to push harder, but that's, I think, something most people wouldn't expect. We're studying the impact of propeller fouling on powering also, and the use of coatings to reduce propeller fouling. You can use like a slippery coating so that the biofouling can't attach. and that really helps. But as the coating ages, it tends to get damaged, and you may reach a point at which it's not helping you anymore. Now it's hurting you, and then you have to do a whole analysis of the life cycle of the coating, because we only have the opportunity to replace it about every 10 years, and so it really needs to be able to last a long time to fit our use case. Uh, Shifting gears, let's talk about cavitation inception. This is a project that the University of Michigan has helped us out with. Uh, Cavitation, for those of you who aren't familiar, it's the growth and collapse of vapor bubbles due to low pressure in the flow field, kind of like boiling happens due to heat. Cavitation happens when you cross that phase boundary due to a change in pressure. It's really noisy, so we don't like it for that reason. Also, it can cause erosion, which I'll talk about later. So we had an arrangement here in our 36-inch water tunnel using the closed jet, which is about 1 meter in diameter. And we had a two-bladed propeller. This shows the overall schematic. Here's a picture of what it actually looked like looking through these windows. And this is the two-bladed propeller model that we have in there. And there's a camera that's located up here in the top window. We were looking at vortex cavitation because that's usually the biggest problem. It happens first, like you saw in the open propeller pictures. Also with ducted propellers, vortex cavitation through leakage through this tip gap clearance is where it happens first usually. It's been difficult to compare simulations with measurements due to lack of directly comparable data. And of course, we'd like to make good simulations so we can design better propellers without having to build and test them so much. Uh, it's been hard to compare the measurements at model scale and full scale because at model scale, typically you have someone looking through the window and flashing a strobe light to make it look like the propeller is not moving, flashing it once per revolution, and watching for these cavitation bubbles. And it has to reach a certain size to be seen by the human eye, and you need to see it with a certain frequency to be sure it's real, right? So maybe they're looking to see it every 5 or 10 seconds. And the question is, how do you compare that with data from a simulation where, maybe you have a void fraction number, right? So what we want to do is stick to single phase to start with and compare the pressure distribution. There's some recent techniques for doing tomographic particle image velocimetry and then reconstructing the velocity field to get pressure, or using the velocity field to reconstruct the pressure information. And so, that's the way we think we need to be able to do it ultimately if we want to have confidence in our simulations for predicting cavitation inception. Developed cavitation, where you have like a sheet of cavitation on the blade, is kind of a different situation. So to plan this experiment, we did a fair number of simulations. We wanted to, number one, make sure that the thrust and torque from the propeller was going to be within our dynamometer limits. This shows the blade here flows from left to right. This is the suction side, the lower pressure side of the blade. Over here is the higher pressure side of the blade. And flow is trying to wrap around through this tip gap here, or sneak through the gap. We wanted to make sure we had cavitation inception in the vortex downstream, not on the blade. You can see that the pressure here is lower. It's the overall minimum, whereas we have a low pressure area here on the blade, but it's not as low. And so that was very important to make sure we had the right conditions for the test. And we wanted to make sure we could suppress cavitation at the design condition. That's, at the advance ratio and tunnel speed we were planning to use. Would we be able to raise the pressure in the tunnel high enough to prevent all cavitation, so that we could then generally gently reduce it and figure out where cavitation started. So we used large entity simulation to do these calculations, and we ended up adjusting the conditions and using velocity that was only 75% of what we had planned, so that we could get these pressures, into the range we needed, and make sure we had the vortex cavitation first. And this is what it looked like through that camera on the top. So you just saw the blade. This is the trailing edge of the blade. Flow is from the top of the screen to the bottom of the screen, and you can see it rotating to the right. And you can see cavitations happening way over here off the blade, kind of like we had predicted, right? It's off the blade. And you can see this bubble exists for a fairly short amount of time. looking at the details of it, hopefully you can, the resolution shows it pretty well to you. You can kind of see, a couple of vortex filaments that the bubble's growing in, and then, sort of combining. So let's look at how that relates to the flow field, that we can visualize using CFD. Here I've overlaid part of the CFD solution for that condition we were just looking at. And here's the bubble we just saw. These colored stream tubes sort of here, or isosurfaces of vorticity, show you where the leakage vortex is, the main vortex that builds up from the flow through the gap, right? The strongest vortex. And then here you can see some other vorticity coming from the trailing edge. Really, there's some coming all along the blade, and it's kind of being combined into this stronger leakage vortex. And what you can see here is that this is kind of in line with this trailing edge vortex and the vorticity that's coming through this gap. And what we believe is happening is that this vortex is being stretched by this stronger vortex. And that's causing, as the vortex stretching is causing a pressure drop in the core. And when a when a nuclei happens to be in the right place, it grows, and we see the vortex like this. But here's a slightly different example. The blade trailing edge is here. It doesn't show up quite as well in this picture. And this is at a lower value of J, the advance ratio. And that essentially means that we have more loading on the blade, and the loading is shifted toward the leading edge of the blade, right? And that makes this leakage vortex stronger. And here it appears that the cavitation is happening first in the leakage vortex. Unfortunately, we don't have a great way of visualizing some of that. So hopefully, once we can compare pressure data, in the flow field with the simulations, have high confidence in the simulations, we can get some more insight into that physics. But I think we can get some insight into that stuff now. I know you have people at the University of Michigan working on that. Where do we stand? Well, there's still a lot of work to do on our experiment. In particular, we want to do planar PIV based on where the simulations indicate we should be looking. And then we'll move on to the tomographic PIV. And once we have that, then we can finally do pressure reconstruction. Johns Hopkins University is doing a similar test with a model that's about 1/3 the size. And they're going to work through a lot of this stuff first at a less expensive facility, and then hopefully we'll be able to do it at our facility using what they've learned. The Australian Maritime College is also involved in this. They're going to be testing a model that's about 2 feet in diameter. So I'll talk briefly about design and analysis methods. I only have one slide on this. I think we're on schedule. So for propeller design right now, we use potential flow methods like lifting line, vortex lattice, and panel codes. Lifting line goes back to like the 1960s, vortex lattice, maybe the 80s, and panel codes the 90s. We use these to get forces, and they have a design mode too, particularly the vortex lattice codes, where you can specify loading distribution rather than specifying the geometry, rather than enforcing the kinematic boundary condition, like you typically do in RANs or LES. It allows you to flow through the surface, and what you're specifying instead is like a jump, and that's really useful in the design mode. For viscous flow, we're using RANs and LES to predict all the same things we're doing with the potential flow codes in greater detail. And they also try and use those for things like cavitation inception and cavitation erosion. Speaking of cavitation erosion, this is kind of the second half of the talk. As I said earlier, it occurs when a liquid changes to vapor due to decrease in pressure. When the pressure goes back up, these bubbles have to collapse, and it's very violent, and it can cause a lot of damage. It's not just a problem for ships. This happens in other kinds of pumps, other situations where you have low pressure in a fluid. Places where we do see it on ships, rudders, there's a swirling flow off the propeller that creates an angle of attack on the leading edge of the rudder, and that leads to a sheet cavity, which starts, fairly close to the leading edge of the rudder and then collapses somewhere around here, kind of near the middle of the chord. the chord being the leading edge to trailing edge direction. And you can see it removes the paint, and eventually it starts eating into the metal. And here's an example on a propeller tip where it's dug a trench, really. I mean, this is, extreme damage. I believe this a hole was here for picking up the propeller blade, and it was supposed to be filled in before the propeller was used at sea, but that didn't happen. And so this sharp edge was the source of cavitation, and there a sheet cavity would have formed going downstream here, and then you can see it collapsed all along here and left a big mess. But this is unusual. This isn't what we normally see. Usually you see something like this pitting that starts here, followed by perhaps a little bit more material removal. So what limits our understanding of cavitation erosion right now? Why is it a problem? And why weren't you doing more about it? Well, we don't understand the fundamental physics really, including things like shock waves, temperature flux, fluid structure interaction. Also, we don't understand how that applies as it relates to coatings. For metals, we have a little bit better idea. Metals are a little easier to understand, but it's really complex, and that the inception problem is very much like solving a single phase flow and just going a little bit further. Whereas the cavitation erosion problem, you have to understand the life of the vapor from when it's created at inception until when it collapses, and that the violence of that collapse and the behavior of clouds of bubbles. It's very complex. I'll show you a video in a little bit. One of the other problems we have is that propellers on ships return from sea with pits due to cavitation erosion, but we can't identify the conditions that cause those pits. The ship goes to sea for 3 months, 6 months, a year. It comes back. Something happened. When did it happen? How do we know? Was it something that had happened during a long run at high speed, or was it something that happened during a really hard turn? We really can't be sure. We do have some erosion measurement approaches. They're used in the laboratory testing. Generally, that's for accelerated testing because if you have something you want to last for 10 or 30 years at sea, you don't want to spend that long testing it. You want to be done in a few days. So the laboratory tests look a lot different, and because we don't understand exactly what's happening at full scale. We don't really have a good way to correlate our laboratory tests with what we can expect to happen at full scale. This was a pretty big project. We had collaboration from the University of Michigan, including Mahesh, Harish, Steve Sescio, University of Memphis, and the Applied Research Laboratory at Pennsylvania State University, U.S. Bureau of Reclamation, and Pacific Northwest National Labs. So we had some government labs, university labs. We had a lot of people involved working on this project. And so what was our approach to try to improve our understanding? Well, we had the unique opportunity to tackle the full-scale problem because the U.S. Navy has a large cavitation channel in Memphis, Tennessee. It's big, and we were able to put a big hydrofoil in there. It was 2.1 meters long, and we were able to test at about 30 knots. Last summer, we got up to 27 knots. In February of this year, up to 35 knots. And so we measured the material properties. I'll tell you a little more about that in a minute. Got pitting data and hydrodynamic flow data. So that's kind of like our full-scale equivalent, approach. Hopefully, we can kind of relate that to what we know happens at full scale. Then we also had the opportunity to perform experiments at 14th scale at the University of Michigan. There's a scale model of our large cavitation channel. It's called the mini LCC. It's at the University of Michigan, and we built a 14th scale foil to go in that 14th scale test facility. And that was great for planning the experiment. And matching some of the LCC experiments there is going to give us some idea of how things scale for when we want to do smaller scale tests in the future. Also, X-ray experiments there at a different facility at the University of Michigan are going to give us volume fraction information that we can use to help validate the simulations. At Carderock and at Penn State University, we're doing some of these laboratory erosion tests. We're we're hoping to create an empirical correlation between the full scale test and the standard laboratory measurements. The G134 test uses a cavitating jet of water, whereas the Pennsylvania State University test in their water tunnel that creates a sheet cavity, more like what we're dealing with here, and that can go up to about 100 knots to accelerate the rate of erosion. Of course, we're simulating the experiments at three of the universities and at Carderock. Initially, we did that to assist in designing the experiment to give us an idea of what angle of attack, for example, we should have the foil at, under what conditions we expected to get a cavity that was about 50% of the chord length. And then we'll be simulating the actual conditions that were encountered in the experiment so that we can learn more than we would from the experiment alone. Because we can, get pressures at more places that we can measure, things like that. And we're also evaluating some materials and coatings to see how they do under this full-scale like flow, even though we can't afford to test them for very long. Large cavitation channel. Here's a picture of the foil in it. It's 3 meters wide. The large cavitation channel is also 3 meters tall in the test section. And the test section is about 12 meters long. So we have a lot of space. There's a couple ladders you can see at the back here for a sense of scale. This is a CAD drawing of the foil. You can see we had 28 locations where we could put material samples. They're in 7 rows and 4 chordwise locations. And then there are also these cover plates where we had pressure sensors, and underneath there were accelerometers. We were taking as many measurements as we could pretty much. We were fortunate to have this model existing from some testing that was done in the 2000s. One of the challenges in this project was that we had 18 months, to get through all the planning, construction, and do the first model test. And so having this on hand was a big help, but it still took quite a while to machine in the pockets and do other planning. We tested a large number of materials under cavitating conditions, and we measured the pitting using both a gel site probe and an optical profilometer. Nickel, aluminum, bronze, and stainless steel were 2 of the materials we tested, but those are really hard materials that are used at sea. They're some of the most resistant to cavitation erosion that we know of, and so we couldn't. If you're expecting them to be damaged over like a 5-year period, we can't afford to run the LCC for 5 years. So we ran it for only a couple of weeks, each time, or maybe 3 weeks. So we also use softer materials. We had nickel, which was kind of intermediate, and then we had a soft aluminum, and we had copper, which we knew we'd see a lot of damage on. We also tested a polymer and some coatings to see how they'd react to cavitation at this scale. We measured the flow conditions, including measurements for CFD validation. Excuse me while I take a sip of water. So some of the measurements we made, this is the LCC test section, flows from right to left on this picture. Here's the foil with cavity on it, notional cavity, about 50% of the chord length. As I said, inside of it, there was static and dynamic pressure measurements, accelerometers. There were some electrodes on the foil surface in our most recent testing. We were measuring the inflow all the time with LDV, and we also measured profile upstream and 2 profiles downstream using LDV to compare with simulations. We had a bunch of cameras capturing the flow and a number of pressure sensors in the windows, both static and dynamic, so that we could look at how shock waves from the cavity collapse move through the section. We also tried a laser vibrometer mounted on the bottom of the LCC to measure deflection of the foil, but the cavitation was so violent it was shaking the whole LCC, and these measurements turned out not to be as useful as we had hoped. So here's a picture of what it looks like. You can see this is pretty dynamic. You can see flow is from left to right. This is the leading edge of the foil. Trailing edge is over here, and you can see this is about 50% chord length. You can see these clouds of cavitation being shut off. You'll often see these vortex shapes. That's kind of normal. And you'll see this horseshoe kind of formation at the trailing edge. You'll see almost like a scalloped approach. A larger shedding event can then lead to some smaller shedding events. You see, again, you can see things traveling through the flow field in both directions. So there's a lot going on. And these are, of course, our material samples. In that video, we were using a fence, which is like a cavitator that we installed near the leading edge of the foil. The fence was essentially a risk mitigation. We wanted to be sure that across those 7 different columns of samples, we would be getting very similar sheet cavitation. And we weren't confident that if we had a rounded leading edge, if there was any variation in the flow field, maybe we wouldn't get consistent sheet cavity. So we started out with this fence because we wanted to be sure that we'd be able to at least get some pitting data. In subsequent testing, we tried without the fence, and we actually were able to get a very consistent cavity in the spanwise direction. Obviously, it's different near the walls, but across our 7 columns, it was pretty consistent. And we discovered that the fence actually made a bigger difference than we expected. You can see the flow here, very turbulent. Really, it looks almost like snow. There's a lot of texture. Over here, you can see that there's areas where the sheet cavity is glossy on top. This is vapor underneath here, and it just has a glossy surface rather than turbulent. And you can see it was quite a bit thinner. And we were able to get some data both ways. So how did we get the pitting data? Well, here's the test arrangement you just saw with the sheet cavitation and the cloud cavitation. Well, afterwards, we took out some of the samples. This is what they looked like. And then we put them on this Keon's optical profilometer. And we measured 3 areas on each sample. We didn't have the time to do a highly detailed scan on all of every sample. So we picked an area near the leading edge, the upstream edge, one in the middle, and one in the downstream. And we consider those characteristic for now. We've been able to retain most of the samples so that we're going to be able to do more scanning in the future if we want to. This is an ongoing project. And counting the pits, we found most of them near midcord, which is what we had anticipated. There was a quick visual count before we started scanning, and then scanning using 3 different thresholds for pit sizes all gave us fairly similar trends. And of course, we did this for multiple flow conditions and materials, some of which I'll be showing you. This is what it looks like in greater detail. These are contour plots, scans from the optical profilometer of those 3 sections. They weren't as close together as this would suggest. There's more space between forward, middle, and aft. Here you can see A is the one upstream, D is the downstream end. And you can see that at the far upstream and far downstream, there's not as much pitting as what we can see here, and particularly here in your 50% chord where we had anticipated the highest pitting rate. That got the most, and you can see there's some pretty big ones too coming downstream of that. So we started with a location dependency test. As I said, we wanted to be sure that all the rows were getting exposed to the same thing, more or less, before we started switching out the materials, because we weren't testing the whole foil filled with the same materials. We couldn't really afford to do that. So we started with the soft aluminum where we knew we would get results. You can see the pits fairly easily with the naked eye. You can see the bigger ones. These are probably some of those big blotches, blue blotches you saw in the previous scans. There's a lot of smaller ones that we can't easily see here, but we're somewhat easier to detect with the scan. And here's a plot across all 7 columns of materials. I would say that within our uncertainty, we are getting basically the same thing. It doesn't, like if we look at column 7 or column 1, which are far to one side or far to the other, we don't really see them standing out much. We do see a little difference in where the peaks are here. We don't think that's necessarily real. For sure, it may be just the places we chose to measure at, and that the real peak is maybe somewhere in between. But in any case, we felt like we were exposing all our material samples across all the columns, at least, to more or less the same thing. So then we went on to testing a variety of materials. You can see we've got the aluminum, the copper, nickel. We had some aluminum ones here that we called sacrificial. They're the ones we used in some of the cavity length tests and things like that. We'd use them as kind of fill-in spaces. And then we had some of the coatings like Interspeed and Hempagard, and we had a polymer as well. And if you compare the results here on the metals, you can see that in general they all had the highest erosion rate at midcord. As expected, the nickel, aluminum, bronze was the slowest. The aluminum was the fastest, and you can see the shapes are kind of similar. And so I think and that we can conclude that our results for the softer materials may apply to the harder materials also. This is some of our earlier results. We'll have a report and a number of papers with the detailed results. We'll be presenting at the Symposium on Naval Hydrodynamics next year. What about the paints? This one, this shows you what they look like after 8 hours. This is locations B and C, as you may recall. Those are the closest ones to midcord. Midcord is somewhere around here, where the most intense erosion was. And you can see after 8 hours, there's a decent number of pits here, and you can see some degradation kind of at the leading edge of this sample. Here, you can see what it looks like after 18 hours. This is now grown quite a bit, particularly in this area here. This area here is we're closer to midcord where the more intense collapse is. And this piece from C7, this, we think what happened is that the front edge of the coating, was damaged enough that eventually the pressure got under there and caused it to peel off. This is what some of these coatings look like on a real propeller, on a real ship. This is kind of thing that's happened. We do feel like this is somewhat similar in the way that it happened. Here you can see there's a tie coat in between the outer coat. Here you can see that in red. We don't have quite the same shape here. So, these are things we can look into. This is a little bit more about the ASTM G134 test. On the right here, this is what the whole test rig looks like. There's a big pump, and it pushes water through a tiny nozzle here into this test chamber, which is what you see here. And it tests the sample. It's only a half an inch in diameter. So, a lot different than what we were seeing there in the large cavitation channel. There are some advantages here. First of all, it's very fast, and we can control the cavitation number and the jet velocity independently. So that gives us a little more control of the rate of the erosion. So how does it compare with what we saw in the LCC? Well, here are the same painted sample at 3 minutes, 5 minutes, 7 minutes. All right, and here's a couple pictures of what it looked like before starting. You can see it wasn't perfectly smooth. It's turned out that painting these, half-inch diameter samples is really difficult to get them perfectly smooth. It was easier to paint the big samples. They use like a stencil type approach for this. But trying to do this better is maybe something we need to work on a little bit. But I don't think it made too much of a difference in the way the erosion occurred, at least, for the times we measured it. You can see there's a little bit of pitting first, and the big removed area, the micro pits, as it says, are the kind of the first stuff, and there's a deep pit here, and then it grows. This 5 minute one goes with what you're seeing here. So 3 to 5 minutes with the G134 turned out to be equivalent to about the damage we saw after 8 hours in the LCC, which is what we showed here, right? In terms of the size of the pits and the amount of damage. So rather than having to put in a whole day at the LCC in that complex setup, maybe in the future we'll be able to do something like 3 or 5 minutes, in our laboratory. It's a lot easier. Saves us about 100 times, the exposure time. So particularly, like I said, if you're looking for something that's going to last 10 to 30 years, you really want to be able to, accelerate the testing by factor of 100 or so. And we don't have the results from the ultra high speed water tunnel yet. So we're going to see how those compare when we get them. Some of the challenges in this project, besides the time and the money, these are things that we, I hadn't considered when we were planning this. Structural limitations were something I hadn't thought about enough. This is a foil we had tested in the large cavitation channel before. It seemed easy enough. We'll just put it back in. But we were at a different loading condition, particularly with the cavitation. And that resulted in a moment on the tangs that support the foil, the walls of the LCC. And we spent quite a bit of time and effort studying that from a structural standpoint. We ended up adding some blocks to support the trailing edge of the foil. Those blocks stick out into the flow and cavitate. They're not ideal given, advanced planning. Maybe we could have done a little better. I think we might have needed more time and money for that. But certainly that was a bit of a surprise. The LCC ceiling and floorboards, there's a quiescent area, at the top and bottom of the tunnel that's separated by these boards. The boards are made out of fiberglass, and they were flexing during the first testing, which is one of the reasons we didn't go any higher than 27 knots. At least the ceiling was. So we added some stiffeners to the ceiling, and those pretty much did the job. We were able to get to 35 knots. But unfortunately, one day before we were scheduled to finish testing, one of the floorboards ripped out and very quickly took some of the other ones with it. So that was a disappointment, but at least we got in all but, maybe 10 or 12 hours of testing from our plan. So in the end, we did okay, but it would have been nice to do better. Quantifying the pits has also turned out to be more difficult than I had expected. We are very focused on being confident that we would produce pits that we'd be able to measure, and we succeeded. The problem is that we want to measure as many of the pits as we can, and so as they get smaller, they get harder to measure. Right now, we're finding that different analysis methods can return different results in terms of the number of pits or the volume of the pits, size. And so, in addition to the commercial software that came with the optical profilometer, which is kind of a general purpose tool, we're also working on a couple of custom tools at Carderock and at University of Michigan to do our own pit counts, and hopefully all three approaches will return more or less similar results, and we'll be able to move forward with confidence that we have a real answer that we can compare with the model scale results. Corrosion on the aluminum samples, which were our softest ones, the ones we were counting on, turned out to be a bigger problem than we expected. Aluminum sacrifices to nickel, aluminum, bronze, which is what the foil is made out of, and also to stainless steel, which is what the LCC is made out of. We attached some zinc anodes to the backs of the aluminum samples. Obviously, we couldn't put them on the front. It wasn't enough. We still got corrosion on the aluminum, and you can see that here. There's all these little red high spots, which are that, and so that's confounded our results a little bit. But it's not something we haven't been able to sort out. Fortunately, it's in the opposite direction from the pits. To summarize, cavitation is pretty complex. We've been studying it for years, and I think we're going to continue to study it for years. It's not a problem we're going to solve anytime soon. It's only one of the several research areas we have in propellers, so it's kept my job interesting over the years. I've worked on a lot of different aspects, and when you get a little bored with one, you can always move on to another. We've been teaming with universities and other departments at Carderock, for instance, the coatings and some of the fouling work or in other departments to improve our propeller designs because we want ours to be the best. And propellers are just one of the broad range of technical areas that we work on at Carderock. I tried to give you a flavor for that earlier, but really it's, we could spend an hour talking about that alone. We do have an educational partnership agreement, as I mentioned, and I'm the point of contact at Carderock. Mahesh is the point of contact at Michigan. So you know us now. And if you want to reach out to Carderock to see if we're working in the area you're interested in, and you can have a conversation with someone about what our problems are, we can set that up, or vice versa. If you're at Carderock and you want to find out about the latest research at the University of Michigan, we can help arrange that too. CNRE is also a forum for that collaboration through presentations like this. I've enjoyed tuning in to the ones from the CNRE, and I wanted to kind of give back with a presentation like this. And we're scheduling, I think, two per semester coming up next year from Carderock, hopefully, to give you a little more information about some of these projects and other ones. Thanks. I'll try to answer any questions you might have.
Thank you, Tad. Thanks so much.
Sorry, I couldn't be there in person. I really wanted to, be there in person because I think it's a little bit better. But
I'm sure we'll see you in person once when you're able to travel. The restrictions are lifted. Questions? Divyansh.
Should I come there?
Okay.
Can you hear me?
Yes.
Now I can. I couldn't hear earlier. But
Okay, thank you. I think you use different cavitation number for model scale and full scale on page 32. I want to ask why do you use different cavitation number or numbers for those cases?
right. So we want the same cavitation number, obviously, when you're testing a geosim and you want to create the same flow conditions. And so that is what we do if we're talking about, say, in the MLCC at the University of Michigan and in the the LCC in Memphis. But for methods like G134, it's more about developing a correlation. You can't expect to test at the same cavitation number and get the same results because it's not a geosim. It's the physics are quite different.
Thank you.
Hi, Thad. Great talk. And my question was related to cavitation erosion. You mentioned that when ships set out for sail for like 3 months or 6 months or maybe a year, and when they come back with these eroded hulls or rudders, you don't really know under what conditions that happened. So would it be feasible to install maybe some sort of a sensor, maybe a camera or a sneakometer that measures sound and that takes measurements throughout the long sail of the ship and tells you that whenever it sees a difference in the image that it captures or the sounds that it's hearing, that in this window or at this place, it's highly likely that erosion happened. Or are you looking into some sort of something like that?
I think that's a good idea. I think sound is tricky because there is a lot of cavitation that doesn't cause erosion. And like the tip vortex cavitation, which starts first, so that's not even on the blade, so it's not going to damage the blade. So I think one of the challenges with sound would be, how do we know which sounds relate to erosion? And I think that's not something we measured during our test, but I think it was so noisy during the test that there probably be hard to sort out the noises that mean erosion's happening from ones that don't. Although perhaps, on a specific ship or something like that, if you had another way of, quantifying erosion so you knew what sound to relate it to, maybe you could. Visual, I think, would be definitely an approach that would work. The problem is, where to put the camera. I think, that's really hard. Maybe for a rudder, if we had a camera in the hull, we could, get a view of it often enough that it would give us a good idea about the rate of erosion. I'm not sure how we could go about arranging to do that type of testing, but I think that's a good suggestion.
Maybe to add to that, maybe we can train some machine learning models on the sounds of erosion so that then we can sort them out. Yeah, I think if we can,
Again, for machine learning, you need a sort of curated, data set, right? So we need to know that we have sounds that contain erosion, and sounds that don't. And so we would have to figure out how to go about setting up that experiment. But I think if we could do that experiment, then that could work. Machine learning would be a good approach.
Ask like what properties make a good cavitation coating, and how exactly do you go about scaling that to for like you're trying to shorten the time that you have to test?
Well, I can't say we really know that. That's what we're trying to figure out, largely because we have these accelerated approaches, but like I said, we don't really know how to relate that to what we need for full scale. Unless we develop something that lasts forever, it's hard to say it's going to last for 30 years, and maybe what lasts forever. Is either super expensive or has some other disadvantages. I mean, we only want to pay for something that lasts the time between dry dockings when we can do it, repaint. So the time element is a really difficult one. As far as what makes a coating better, I'm not sure, just because we don't understand the physics that well. The Bureau of Reclamation has a coating that they're testing in hydroelectric applications, and so we might be able to find out from them what they think is an important aspect to the coating. But our other challenges with coatings, at least in our application, is biofouling, because whatever we put on the blade, in addition to resisting cavitation erosion, it also has to either resist biofouling or be something that we can scrape clean without damaging it. That's been one of the big challenges so far, is that we've have these two requirements which maybe kind of go in opposite directions. Well, or not opposite, but they may not be complementary.
I was wondering, like, is there any research testing, like, with biofoul surface you subject to cavitation, whether there's potential of using cavitation to scrape off the biofouling?
Yeah, that was an idea that was developed to essentially use like one of those cavitating jets, like you saw in that test setup, to remove biofouling, and it is effective. But can you do it without damaging a coating? Or would it be more gentle than other approaches? I don't know. I can say that it hasn't taken off, all right, but it is a possibility. Cavitation is a good way of removing biofouling. In fact, we really don't have a problem with biofouling on our propeller blades in the areas that see cavitation erosion, right, or intense cavitation. It's easier to remove the biofouling than the metal. So, often that comes off. The tube-worn bases and so forth don't stand up to cavitation very well.
So you mentioned the advantages of counter-rotating propellers, but would the cavitation be worse in localized low-pressure regions, like between the blades when they rotate, or when the tip vortex of the top interacts with the bottom, especially when you are turning the bottom propeller? That does that outweigh the advantages?
No, I don't think it has to. You can definitely come out more efficient, and I don't think it necessarily makes cavitation worse, because you're distributing, what I guess would be a slightly smaller pressure difference, right? Because the thrust comes from the pressure difference times the area, and if it's more efficient, then maybe you don't need quite as much area or quite as much pressure difference. So I don't think it makes the cavitation worse. You can worry about the interaction, though. That's one of the reasons for having the downstream propeller diameter a bit smaller. Also, the slipstream from the upstream propeller contracts as the velocity accelerates. That's the other reason for having the downstream one smaller. But you do try to make the downstream one avoid interacting with the tip vortex from the upstream propeller. But if you did have a lot of cavitation on the upstream propeller, that could cause a problem for the downstream propeller potentially, if you have vapor cavities that are then going onto the pressure side of the downstream propeller. where the pressure goes up really fast, that could be a problem. So I think that's going to be application dependent.
So just a follow-up question on that. On like if you have a counter-rotating propellers, can you reduce the conditions which induce cavitation on one propeller by having two of them operating at slower speeds?
Yes. Yeah, reducing speed helps, and somewhat, and certainly anytime you increase area, that really helps with reducing cavitation, because then you don't need as large of a pressure difference. So that brings up your minimum pressure.
Any other questions for that?
How many personnel do you need to operate the LCC? And like, what's the operating cost?
I can't speak to cost, but I can tell you that we've got 2 operators, who sit in a control room at all times. So you absolutely have to have them. That doesn't necessarily allow you to actually get any measurements, though. So typically we have maybe 3 to 10 people taking measurements, depending on how many different things there are to collect. And then the LCC has other staff, who are there in the building.
Other questions?
I have a question.
Yeah.
So do you have any kind of simple mathematical models on pitting formation? For example, from the simple model, we can clearly see which parameter will be dominant. Any parameter from material to resist the pitting, or any other factor that can cause pitting, something like that.
Yeah, well, certainly for metals, I think we have a decent idea. My coworker, Jin Kyun, could speak to that better. And, I'm hoping we can get him to, give a talk in the fall or spring of next year. So hopefully, also we'll have papers, showing our conclusions from this. So I'm gonna leave that question for him to answer.
Thank you.
Thanks, Thad. Okay, if there aren't any more questions, thank you, Thad, for taking the time and for giving us a great talk. Thank you much.
It's been my pleasure. Thanks for hosting me.